评审还有那个排队老师大家好。那我们现在准备要开始我们这个 Round 5的这个 Physics 5之前，容我先提醒大家一下，就是各队呢，还有我们所有这边的人员呢，不可使用网络，不可录音，不可这个摄影，好，请大家遵守这个规则。然后另外呢，参赛的队伍呢，你们在投影机前面不要保持灯光。那容我先来介绍今天的这个评审啊。那先介绍第一位是中亚研究院的黄宗海老师，第二位呢是我们师大的古老师，第三位是清华大学郑一凡指导，还有我们台科大陈宏仪不好意思，陈老师。是清华大学刘大明，他今天来提答服务哈。好，那我们就准备接下来就要请各队来介绍自己。Let's welcome our team to introduce your team and team members. So starting from the podium, please.
Good afternoon. We're Me One from Taipei Weigel Senior High School. Me Two from Taipei Weigel Senior High School. And I'm Yu Dongyue. This is Wang Lian. This is Ding Muyun. This is Wang Xuanqi. And this is Liao Zheyu. Thank you.
Good afternoon. We are team two from KGHS. I'm Yang Yuyi, Chen Youqi, Chen Qianhui, Chen Xuanci, Mo Wenxin.
My name is Alex, and I'm from the Pingtung Gaozhong. And my name is Wang Dongqing. This is Su Bingqian. This is Wang Chen. This is Zhang Jiasen. And this is Zhang Semin.
Hello, welcome to your team Alphas from Qincheng High School. I'm Wang Zhen, Xie Chengxuan, Zhang Yuanzhen, Ye Xuanyou, Ji Kaiting.
Right. Welcome. Right, so now we start our physics fight. The opponent challenges the reporter for the problem. 1 minute. Okay, so the reporter accepts or rejects the challenge. 1 minute. 他们不用 Yeah, sorry. Alright. So, should we just... Okay, so please write down the reporter, opponent, and reviewer's reaction.
Honorable judges and worthy debaters, this is a reporter from Me2, reporting problem 13, charge meter. So let's start with the problem statement. The lightweight ball is suspended from a thread in the area between two charge plates. If the ball is also charged, it will be deflected to one side at a certain angle. What is the accuracy of such a device for measuring the amount of charge on the ball? Optimize your device to measure the smallest possible charge on the ball. So today, we're going to focus on explaining the phenomenon, improving the device for accuracy, and finding out the smallest possible charge. So here's the phenomenon. The ball is deflected to a certain side due to the electric force caused by the charge plates. And a positive charge pole will be deflected to the negative charge plates. And the opposite, negative charge pole will be deflected to the positive one. So this formula shows the electric force that affects the ball by the charge plates. And so this is the phenomenon. And the electric field between the two charge plates causes the electric force that makes the ball to deflect. So before we conduct every experiment, the thing we have to find out is that the electric field between the charge plates. Since the charge plates aren't infinity, so there might be side effect in that the electric field might not be uniform totally between them. So therefore, we conducted this experiment to make sure that, to investigate the electric field between them. So this is our result. The blue lines are the potential, electric potential between the two charge plates, and the red ones are the electric field. So as we can see, in the middle, right middle, between the two plates, the electric field is close to uniform, so that we can consider it uniform when we conduct our following experiments. So there's another concern about the high electric field we used in our experiment, that is ionized gas. So when the humidity is low, and if the electric field is larger than 3 million volts per meter, the gas between the two plates may be ionized. So therefore, in our device, the electric field varies between 300,000 and 600,000 volts per meter. So the gas between the plates won't be easily ionized. So we are going to make sure the accuracy of this device. So before we conduct our experiment, we have to know the theoretical charge of the lightweight ball. So as I just said, we ignored the side effect since the ball is in the right middle of the two plates, and the capacitance of the two plates can be shown by these two formulas. And through calculations, we can find out the theoretical charge of the ball, which is shown by this formula. So first, we use the deflected angle to measure the charge of the lightweight ball. So here's the force diagram of the lightweight ball, and we can calculate the charge of it by this formula. And however, in order to optimize the device and make the accuracy as high as we can, we use the ball's pendulum period to estimate its charge, since estimating its deflected angle has low accuracy. And while slightly swinging with the effect of electric force, the ball will have an apparent acceleration which is larger than the gravity, so that we will get a new pendulum period affected by electric force, which is T prime, with the larger acceleration than the normal period of pendulum. And so we can calculate, this is the calculation of the charge of the lightweight ball. And after calculation, we can find out that the charge of the lightweight ball is shown by this formula. So here are the relevant parameters that we think may influence the accuracy of our device. And first is the distance between two charge plates, which influences the capacitance and theoretical charge of our lightweight ball. And this is our size of charge plates. And we modified our length of string to calculate the different period of pendulum, and also the radius of the ball and the mass of the ball. And also we controlled our temperature and humidity to make sure that the experiment is precise, since temperature can greatly influence the electric field between the charge plates, and humidity, like I just said, if it's in a high humidity, the air may be easily ionized. So this is our experiment setup. We use a fishing line and hold a metal lightweight ball between the two charge plates. And we use a DC power supply with 30,000 volts to provide a high electric field. So here's an experiment of the string length. And as we can see, with the longer line, the larger swinging range causes different electric field between as the lightweight ball string swings. Like I just said, if the swinging range is too large, and the electric field might not be uniform, so that we can see the error of it is pretty high. And also, with the shorter line, the shorter period of pendulum will increase error, so its error bar is larger than this one. So after this experiment, we can know that the 0.818 meter of line is the best. And here's the experiment about the ball's radius. And we can see, as we can see, the radius of the ball influences the area of the ball, which also influences the air resistance that influence the speed of the ball. However, the air resistance is so small that we can just regard it negligible. And here's the ball's mass. The influence of the normal force is irrelevant since the friction is negligible. And that is because we use a green tack to make sure that our string is greatly attached to our bracket so that it won't move and we can ignore the friction between them. And as we can see, the one with larger mass has a larger error. That is because with a larger mass, the influence of electric force will be decreased. And here's the experiment of the distance and we measured the electric field by angle. And like I just said before, measuring the charge by angle can have a large error, and it's both imprecise and inaccurate, since measuring the angle isn't easy for us. So therefore, we conduct the experiment by measuring and investigating the period of pendulum. And as we can see in this chart, when the distance is lower than 9 cm between the charge plates, the error is very, very small. And when the distance is larger than 9 or even 10 cm, the error is pretty high. So we can, from this experiment, we can know that the smallest possible charge that we can measure of the lightweight ball is around 700 picocoulomb. So here's the graph of the experiment that we changed the distance and measured it by the period of pendulum. And as we can see, the accuracy and precision are both high. And the minimum charge of the ball is estimated to be this. So in order to prove that measuring the charge by period is more accurate, we compared the two experimental results together, and we can see the blue one, which we measured by the period, is much more accurate than the red one, which we measured by angle. So here comes the conclusion. For the accuracy, using angles to measure the charge will have a large error, since it's hard to measure it precisely. And optimizing the device by investigating the difference of pendulum periods, and we found out that the accuracy is about 95.36, and the data came from the chart we provided before. And for the smallest possible charge, like I just said, the smallest possible charge of the lightweight ball that can be measured is about 700 picocoulomb. And so here's the data of the optimized device. The distance between the two charge plates is about 5 cm, and the length of the string is 0.18 meters, and the mass of the ball is 0.27 grams, and the radius of the ball should be 4.325 millimeters. And we use the period of pendulum to estimate the ball's charge. And that's it. Thank you.
Questions? Hold on, and answers the 2 minutes.
First, what's the meaning of you optimize the device by investigating the difference of the pendulum period? You mean the ball will just like a pendulum?
Like I just said, switch the page. When a pendulum of the ball is influenced by the electric field and the electric force, the apparent acceleration will not be the same as the ball swinging without the effect of electric field. So the G prime will be larger and the T prime will be smaller. And we can use the ratio between of T prime and T to measure the charge of the ball.
So you mean the period is the ball moving time?
The pendulum period. Do you mean?
The pendulum like this?
Yes.
But so you think the ball will moving like this?
Oh, sorry. That I didn't explain it. It's that we use a non-conductive ruler to let the ball swing.
Swing?
We attach the ball to the charge plates, and then let the ball be charged, and then release it so it will swing.
So now, how do you control the charge of the ball?
Like I just said, we attach it to the charge plates, and as the time is long enough, and the electric density of the ball will be the same as the charge plates.
one side at a certain angle. And this is the point at the both charges of the both plates. And next part is the accuracy of such a device for measuring the amount of charge on the ball. And this is a question mentioned about optimize your device to measure the smallest possible charge on the ball. This is your structure of solving the problem. First, you observe this phenomenon. Next, you have theory. Finally, you use the experiment to prove your theory. Then this is the performance of the reporter. Your theory is normalized against velocity, and your parameter infers the distance between the ball and the plate. And that is the ball radius, and that one is the ball mass. It's the performance of reporter. First, relevant modeling of the theory, and graph to explain the theory and good time management. And I suggest that you don't have enough parameters, and for explanation on the theory and depth of explanation in the data, and for explanation of the theory and huge error bar. Okay, so I have 5 points I want to discuss. And first is the ball position, and next is how to define the accuracy. And the main point is the charge of the ball. And fourth is the different length of your distance between the ball and the plate, and also the string length. And that one is your experiment method. I think there's a big problem of it. So I can invite the reporters to discuss with me. Okay, first I want to let your report what to do. Can you turn to page for experiment setup? And of your angle, you don't want to measure the angle, and you use the ruler to control your screen and know the period. That page.
This page?
Yes. First, I want to know you use the ruler to control the ball, to move the ball, or to move the string.
Of course, the ball. Since if we want to charge the ball, in order to control the charge of the ball, and so that it can fit our theoretical charge, so we attach the ball to the charge plates, so that the electric charge density of the ball will be identical to the plates, and so that we can make sure that the charge of the ball is controlled every time.
So the method you use is to move the ball and let it free flow, and caused by the force of the magnetic, the plate.
I'm sorry, we didn't let it free fall. We let it slightly swing as a pendulum between the charge plates. I mean, right in the middle of the charge plates, so that the electric field will be close to uniform.
And next, I want to discuss and how do you make sure the string won't rotate?
So we use 2 cameras to observe the ball, and for the experiments that the ball rotates, and we will eliminate the experiments. So we only keep the experiments with the ball rotating, swinging only in one direction.
So in your experiment, although the ball is swing and the force that the plate give it, it won't let it to hold on the angle.
Or can you rephrase it?
That means when you use the ruler to let the ball swing.
May I use the backboard? These are the charge plates, and this is the ball. So we use a non-conductive ruler to let the ball attach, so that it can be charged by the charge plates, like I just mentioned.
Oh, that's a big problem. I think you can measure it.
Like I just said, we can measure the capacitance and the charge density of the charge plates by using the formula I provided on my presentation. And after the ball is charged, and we will release the ball and carefully so that it won't swing at a large range.
This is your experiment. Right?
Yes.
And you attach the plate and charge the ball. Next, you use a ruler to calculate, and next you take out the ruler and the ball will swing to another direction.
Yes, but the range is not that large.
You will that part.
So if here's the ball, and we won't just release it. We'll let it slightly slow. We'll slowly put down the ruler and make sure that the ball will swing under 3 degrees. So the swinging angle is under 3 degrees, and we make sure that, so we can make sure that the electric field is close to uniform, like I just mentioned. So here's our theory. So, like I just said, using and measuring angle may not be precise. So, however, by measuring the period of pendulum, will be much more precise. And so here's the formula, and this is the apparent acceleration of the charged ball affected by the electric force. And here, this is the electric force, and this is the gravity force. And we calculate it by these formula. And this is the pendulum period affected by electric force, and this is the normal pendulum period.
Next, this is your experiment method, and I want to ask, how do you charge the plate? By the battery?
Yes, by the electric DC power supply.
And how many watts?
Like I just mentioned, 30,000 volts.
30,000 volts. So if that is a big number, right?
Yes.
So if that is a big number, the force that gives to the ball will also be, right?
Yes.
So how can you not measure the angle if it will be small?
Can you switch to the problem statement? So that, as you can see, the angle is here, and as we measured it, the angle is around 7 degrees. And yes, of course, the angle is large enough for us to measure. However, the target of this problem is to optimize the accuracy. So after we use the angle to measure the charge of the ball, we found out that measuring the angle isn't accurate. So we changed the method to achieve the goal of optimizing the accuracy.
Okay, so
That doesn't mean that we didn't observe the phenomenon.
So you also improve your experiment by this way. Okay.
Yes.
So next I want to discuss about that your control variables, because your independent variable has two, both radius and also the both mass, right?
Yes.
But how did you, when you change the both radius, do you also change the both phase?
Actually, the density of the ball, the mass density of the ball aren't the same. So that it doesn't mean that if we change the radius of the ball, the mass of the ball will change.
So you think the density of the ball won't affect this result?
Since the thing we're using is to measure the charge is the density of the charge, and it will be identical to the charge plate that we attach to it. So in order to measure the charge of the ball, so actually the mass of the density of the ball doesn't affect, and the formula was the T.
But how do you change the density? Is that different materials?
We use different materials.
But it's not inverted.
Sorry. Actually, we use aluminum, and so we made the bolt by ourselves and make sure that it has the radius and mass that we want.
So first, if you change the radius, also that's in your data, both mass and both radius.
Yes, of course. But
There's 2 points. One is the iron material, another is aluminum material.
yes, of course. And
But
so the mass is the parameter. No, that last page. So this, we know the mass of the ball before we conduct the experiment and get our results. So these are all already known by us, and so it doesn't actually affect the correctness of our theory.
however, if you change the materials, do you think the materials also affect the result? I think that.
So actually, the charge density won't greatly vary as long as the material are all
I
conductive.
don't mention
And
about now it's not the density question. I mean, you change the materials. First is the iron material, and next is the aluminum material. Do you think that it is
we
something?
didn't change that to the iron material.
So
So-
also aluminum material,
Yes.
and how you change the density?
So as I just mentioned, we use aluminum.
You make the ball by yourself.
We made the ball by ourselves, and the ball isn't completely. We use aluminum foil to make it. Yes,
Still,
foil. Foil.
do you think that will affect? Oh, okay, I understand. And next, and your experiment method, you change the degree and under 3 degrees, right? You use the ruler to
Yes.
calculate. And so that is your experiment. But do you think you use hand to control?
Actually not. We use Arduino. The robot, so that the manual error will be decreased.
Okay. And next, do you think that the charge of the plate will affect the result?
Charge of the plate. So actually, yes, but we have controlled it since viewed by our RC circuit charging formula, and the resistance, as long as the resistance is really small, and the time is large enough, so the charge will be controlled.
And this is my summarized time. And now, but I think there is some experiment mistake in his experiment. First, if you want to change the radius, you also change the mass, but if they claim that, they do the aluminum ball by themselves. But I think they also change some the density of the ball, and I think that will cause the experiment different. But they claim that is correct. And next, if they use the ruler to control it, but that is their theory. I don't want to point out that mistake, but I understand. And next, they only have 2 data. I think their data is 2. If you can make the aluminum ball by yourself, I think there's more data you can produce or do more experiments to prove your theory. And then this is my summarizing.
You say you use the appearance of the pendulum to calculate the charge. Can you, as you will observe, the ball will remain moving or it will
controlled to be very small, and the pendulum period will be identical, even though the time passes.
So you control the plate charge too. Then the angle is small.
Can you rephrase it?
Oh, never mind. Opponent, you think about you use the ball will keep moving or stop moving.
I think in this experiment, I think there's not this situation. But if you just use the experiment that the problem asks, I think it will stop at the position.
Okay. And then your experiment 1, you change the length of the string. And how it affect the experiment? And are you consider the string will be charged too?
So as long as the string is non-conductive, and actually the fishing line doesn't attach the charge plate, so that it won't be charged.
Oh, you use the.
And also the mass of the string is negligible, and since we have measured it.
And the mass and the radius will change the gravity or electric field or other. You
So
explain it and connect with your theory.
Okay, so as the formula shows, and the mass will influence the ratio between the period of pendulum. And however, the way we measure our charge doesn't change, since the mass is considered in this formula.
Okay. The radius and the mass, how affect the results?
In this experiment, I also mentioned about this, and I think the main effect.
Sorry, time's up. Thank you.
So here's the concluding remarks of the recorder. So the first, as I just mentioned during the presentation, and the optimized device is shown here. And during the discussion, the opponent asked me whether the density of the lightweight ball influences the charge we measured. However, the period of pendulum will be affected. However, the charge density won't be affected since it's attached to the same charge plates. And also, they measured that the ruler will be charged, and in our opinion, as long as the ruler is non-conductive, it won't be charged, and the ball won't actually lose its charge since it's fully attached to the charge plates. And also, they mentioned that the reason that we use the pendulum period to measure it is for the purpose of optimizing the accuracy. And we did observe the phenomenon of the deflecting angle. However, we regard it as inaccurate, so therefore we used the pendulum period, the ratio of pendulum period to measure the charge of the lightweight ball. And that's it. Thank you.
Right. For questions for jury? Questions? Okay.
I have a question to the reporter first, and then for reviewer and opponent. So for the reporter, can you use 20 seconds to explain again how you find your optimized distance between plate and the stream length?
So the distance, as we can see, the error of this group and this image. As long as the distance between the charge plates are smaller, and so that the capacitance will be larger, and the charge density will be larger, so that as long as there are more charge in the ball, and we can more clearly observe the difference of the period of pendulum, and we can see the error bar is smaller than these three groups. And for the length, this one. And since according to our experience and experiment, and we found out that these three groups have the larger accuracy, and the precision of the 0.818 group is the largest. So we choose the length of the string to be 0.18.
Okay. So the question for the opponent first. So do you agree the conclusion and the experimental setup?
I didn't agree.
And what's the reason?
Yes, in my opinion, the main parameter of this experiment is the charge of the plate, and next is the distance between the ball and the plate. But in this experiment, I don't know, he didn't mention about the main parameter, and also I don't know how did he do the ball by himself, and I think it will not uniformly. And next, I think it will affect the E negative, and maybe the ball will not affect by the force uniformly.
And for the reviewer, the same question. Do you agree the conclusion and the experimental setup?
I think the math is not an important factors affect the experiment, because in my opinion, the ball finally will stop at a position. So he used the lens to calculate the period, but I think it will stop. So I don't think that is a important factor.
experiment use the styrofoam ball and the aluminum ball, right?
What?
In your experiment, you use the styrofoam ball and the aluminum ball.
Yes. No, it's just aluminum.
So all your measurement use the aluminum ball. So
I
you didn't use any styrofoam.
we made the ball by aluminum foil, and we measure we changed the hardness, I mean the density of the ball. However, due to the shell theory, and it doesn't actually greatly affects the charge density of the ball.
One question for the reporter. So you mentioned that you want to keep the swing angle small. One reason is that you say that when your field is uniform. Is that the only reason? Is that the only reason?
Also, as long as we are going to measure the pendulum period, and we have to make sure that the swinging angle is small enough so that the error can be decreased. So that the sine theta will be close to theta.
Please read us prepare our remarks. Right, so jury, please show the remarks for reporter. 7, 7, 5, 7, 7. And the remark for opponent. 7, 7, 5, 6, 6. The remarks for reviewer. 6, 6, 4, 6, 6. Right, thank you, and that's 10 minutes.